Joao will tell us about how to test MOND with solar system.
Okay, well, I understand this is a recently introduced humiliation enrichment. And if you write a paper, you have to give a talk without preparation. Not much notice. So I should apologize in advance. It's not going to be very comprehensive. I'm going to review some aspects of MOND, some observations. I'm not going to talk about everything. And just to give you a flavor. This is based on this statement, and it's essentially, the second half of the talk is going to be exactly about what I think is going to be the crucial experiment or observation, the psychic being dark matter for modifying gravity, and I think that solar system experiments or ground-based experiments. So I don't know if it upsets you, and I don't know if you've noticed, but it's very strange, and I find it very upsetting that everything in the sky, if you look up at the sky, everything except the planets that does not satisfy Newton's laws. So everything you look around you is rotating, is moving in a way which conflicts with Newtonian dynamics, or by extension, with the theory of general relativity. So the solar system is just about the only thing we can see which actually satisfies our dogma about relativity. And if you work in this area, particularly like try to quantize gravity or something that ambitious, I think it should be of concern to you because you may be trying to quantize the wrong thing in the first place. The classical theory could be completely different.
So you don't need to go forward because Joe Taylor might be himself.
Okay. That's another going to be comprehensive. No, but I think there is an issue also, that's a different matter. So basically, there is second postcard with other things. Yes, there are tests of relativity, but I may have time to go into it. It's not that discriminating. So I mean, the thing which worries me is that even before we go to issues of gravitational radiation and so on, Newtonian, non-relativistic Newtonian gravity doesn't seem to be exactly what is out there. I mean, that's the point.
There must be talk about it. I could talk to the talk about it.
Okay, so this is exactly the.
I think I hate them too.
Either you say gravity is fine, and that all you have to do is introduce a new component of matter which you've never seen into dark matter. And some people have called it, Johnny's are probably going to call it the ether. So it's like introducing something which no one has ever seen, which is basically being hammered into the theory, into the observation, so that everything works fine. I think that's a bit slanderous. I mean, it's not that bad. I think there are other problems with dark matter, as you'll see. It's not just an ether, but also it has other problems. Or else, this is the worrying thing, it could be, as I said, that there is indeed no dark matter, and the thing you need to do is actually what the observations are telling you, is to modify gravity. So this is really why this should be of interest and of concern to everyone. And just to be a bit historical, I think this is a good example because I'll be talking about the solar system for most of this talk. Historically, both approaches have been, in turn, successful and disastrous. So you should never take anything for granted. And this is an example, a Leverrier, and it's perhaps the first person who introduced dark matter successfully and unsuccessfully. And you probably know about the prediction of Neptune. Neptune was a dark matter component for quite a long time. And this is actually, there's quite a long story. People believe firmly in Newtonian theory. And the problem actually started with Saturn. The Saturn orbit was wrong by 5 sigma, more than 5 sigma, by quite a while, for about 100 years. So the way actually Kepler's laws apply to Saturn is completely wrong. And like for 100 years, no one cared about this because Newton was a bit right. And it was only like the guys Laplace and people who introduced perturbation theory finally understood that the reason why Saturn isn't exactly going according to Kepler's laws is because of the perturbation of Jupiter. So the whole theory of perturbation theory in the solar system started off as an attempt to actually explain the fine detail using Newtonian theory. And the fact that Uranus wasn't going exactly according to what it should, even when you put all the perturbations in, led to the introduction of Neptune before it was observed. And as far as I know, this is the first example dark matter was introduced to save Newtonian theory successfully, because actually it was observed later on. Now, as I said, this can also be a disaster, and a few years later, he actually tried to predict the anomalous period of Mercury precession, introducing volcanoes, a planet inside, getting near the Sun, inside the orbit of Mercury. And so close to the Sun we couldn't see it because it was kind of blinded by the Sun, so to speak. And as you know, this is a completely wrong way to do it. I mean, actually, this was what led to the theory of general relativity. And this anomalous precession is actually quite important. By the way, the precession is about, the actual perturbation theory precession is about 10 times bigger than the relativistic correction. But that has been taken into account when talking about the residue. So be careful, that's basically the moral of the story to take from here. As I said, I'm going to just give you a very short breakdown of the facts. And dark matter, we did dark matter in many different situations. So just to kind of give you a breakdown, not going to be comprehensive as I said, we need it in galactic dynamics, in cluster dynamics, in lensing, and in structure formation, mainly. I mean, there are some small things here and there, like velocities and so on. But it's mainly the 4 different levels in which we did dark matter to explain how things move around with relativity. So it's this extra component which we need. Let me talk about galactic dynamics, because that's really the thing which led to MOND in the first place. So the basic facts are the following. Fact number 1, as this picture shows, the rotation curves of galaxies tend to flatten. You tend to end up with an asymptotic velocity, which is a constant. So if you look about the rotation of Sun, this is not general, so we're talking about these galaxies. So normal surface brightness disks, things like that, ordered rotation objects. What you find in these guys is that as you go out in distance, the velocity tends to V infinity, which is a constant. And if you just take the photometric data and you say that everything you get is what you see, then of course you're outside the matter inside the galaxy. So you would expect this to be true. So I'm going to write this F over M equals A, because we're going to modify Newtonian dynamics, and I mean in very basic level Newton's second law. So this is the force per unit mass. The acceleration is V squared over R, for something which is rotating in a circular orbit. And of course you'd expect V to be proportional to 1 over the square root of R, to fall off. And it doesn't, it actually just flattens instead. So this is strange, and this happens basically with every single galaxy which has this feature.
Before you go on, can I ask a question about the last slide? Since that's the largest galaxy I've ever seen, I'm just wondering what it is.
I had it somewhere, and I can tell you later. It is bigger. Let's show it on purpose, just to make the point. So I'm going to show you lots of others. This is normally not this dramatic. Okay? This is just to make the point. Second thing, Tully-Fisher relation. There's something really strange, which is, so to speak, oops, there's a problem of interference here. This is an empirical law which basically tells you what these terminal velocity is as a function of the mass. So you just find that this terminal velocity to the 4th is proportional to the luminosity. And this is an empirical law. The scatter is extremely small and is actually explained by experimental errors. So it looks like actually the deviation from this power law is actually very, very small. And probably it's exactly luminosity proportional to terminal velocity to the 4th. And the third thing, which is quite interesting, is that, well, you can show this from the rotation curves, or from the Tully-Fisher relation. You actually find that if you try to plot when do things go anomalous, when do things go strange, or what is really this proportionality relation, what does it correlate with? If you try to correlate that with the size of the galaxy, you find no correlation. The thing which appears to be crucial is rather the acceleration. So for example, this thing which appears here is somehow related to an acceleration, and the point where deviations in detail from Newtonian gravity are felt is not found at a given distance scale, a certain number of megaparsecs or kiloparsecs in these days. It's actually found at an acceleration scale, and the acceleration seems to be important. It's 10 to the minus 10 meters per second minus 2. So it's a very strange thing. Normally we're used to finding anomalous behavior at high energies, at high velocities. In this case, it's the opposite. We find anomalous behavior here when the acceleration drops below a given acceleration, a given threshold. So as you go out in radius, of course, the acceleration goes like 1 over r. Eventually, the acceleration drops below this threshold A0, then things start behaving strange. So there you are. This is essentially the idea which dark matter has trouble. These are the observations which dark matter has trouble explaining. Obviously, you can explain them by postulating that there is a halo, an extended halo, and now I'm going to give you the folklore and then work a bit around it. But the folklore, like some 20 years ago, 10 years ago, was that there was some kind of roundish halo surrounding every galaxy. And the idea is that if you postulate that the mass in this dark matter halo grows like r, i.e., if the density profile is something which goes like 1 over r squared, then clearly you have an extra r here, and the r stays allowed, so you get flattening of the curves. So this is the kind of behavior you need in dark matter to explain why is it that you have the flattening of curves eventually. So there are several problems with this, and okay, to be honest, to be fair, I should say this is exactly where dark matter fares the worst. So, I mean, I'm trying to be fair. In other cases, dark matter is very successful. It's extremely unsuccessful in this particular case, which is explaining rotation curves. So problem number 1 is, of course, is this thing stable? It's not very satisfactory to go around and paint the universe in dark matter every time you need it to explain why gravity should be Newtonian. Of course, this thing will be under the effect of gravity itself and should be stable under its own gravity. And what happens is it's not stable. These guys called isothermal halos are actually not stable. What they tend to form is something which goes like 1 over r cubed at the very center. It's very cuspy in the middle. And then actually goes like 1 over r instead of 1 over r squared. So getting flattening is something which typically people say maybe this happens in between 1 over r and 1 over r cubed. There's a region in which you are 1 over r squared. And it's actually extremely difficult to get an n-body simulation to produce dynamically and under gravity a profile of dark matter which explains this.
Does this depend on the assumption that it's isothermal?
Say it again.
Does it depend on the assumption that it's isothermal?
The equation of state. No, it seems to be kind of a general feature. So isothermal is actually normally stated as the profile.
But the problem with custom is best seen in low surface brightness galaxies, which have an area, low area brightness. So the way it doesn't work in body simulations, and also for 2-parameter profile fits on low surface brightness galaxies, dwarf galaxies. So what they've done is say that the halo is triax. So they introduced another parameter, and the 3 parameters different for each galaxy. You can fit all the low surface brightness galaxies. No surprise.
They could be right. And it could be that every galaxy is different. We're all different, right? So it could be that everyone has a different chemistry. So it could be that these various parameters dynamically evolve differently in different galaxies. I also find it very unsatisfactory, but as I say, and to be fair, this is the point in which dark matter fares the worst. Everything else is actually much better.
You can't falsify it.
That is true, yes, but okay, well, I agree with you, but I think the problem is until you see the opposition, you can't really appreciate the benefits of dark matter. I think you really have to do a calculation in MOND to actually appreciate the benefits of dark matter. And then I think that's what I'm going to say next. It's quite difficult actually to do things like structure formation and CNV calculation.
Third peak.
Yeah, except lots of peaks, anyway. Okay, anyway, the point of this talk is actually that, well, before I say that, there's 2 other problems even before we go there, which is these and these remaining theories. I mean, why is it that the thing, which is a proportionality constant here, between the mass and the radius, is related to the luminosity? Which is a feature of the halo, which somehow is coupled to the luminosity, the visible mass, according to the Tully-Fisher relation. It's a mysterious tuning. We need a lot of fine-tuning to explain the Tully-Fisher relation in dark matter scenarios. And also point number 3, why the hell the acceleration? And it's quite mysterious. I mean, I would expect a length scale to appear rather than accelerations. But maybe it's a proxy for something else which no one really understands about dark matter scenarios. So it's a bit of a black box, to be honest. It's a bit of a black box. And as I said, this is the point where dark matter fares worse. Everything else is much better than this. So the point where the other alternative fares better is actually here. This is what led Milgram to introduce modified Newtonian dynamics. The idea is to consider 1, 2, and 3 as the Kepler's laws for a new theory of gravity. So we found out about Newtonian gravity from Kepler's laws. This is how Newton derived his law of gravity. Given that nothing around us seems to satisfy Newtonian gravity, maybe we should just look at the kinematics first, infer something like Kepler's laws, that's 1, 2, and 3 for galaxies, and try to find what can we learn about the theory of gravity from this. And modified Newtonian dynamics, MOND, is basically this exercise. And let me just give you this in a kind of summarized way. So the basic point initially was something which is a bit of a joke nowadays. It doesn't work, I'll tell you why, but it's basically the best way to introduce it. It could be that force is not doesn't equal mass times acceleration. It is only true for high accelerations. So this is only true when A is bigger than A naught. It could be that when A is much smaller than A naught, you would rather that force over M is A squared over A naught, where A naught is the new fundamental acceleration, new fundamental state. So this is the kind of inference we derive from these Kepler's laws. You basically find it's very easy to show that this, what you have is Gn over R squared, the usual force, is now equal to going to be 1 over A naught V4 over R squared. The R squareds cancel, so you have flattening of curves. By construction, point number 3 is, of course, the threshold between Newtonian and non-Newtonian behavior. The Talley-Fisher relation is immediately true, because now, of course, mass is proportional to luminosity. What you see is what you get. There's no dark matter, so all the matter you get is basically the visible now. So from the luminosity you get the mass, and therefore v to the 4th should be proportional to luminosity. So this is the very naive starting idea. The question is, what do you make of this? It's quite a complicated thing, really. It's much better than what it sounds. And in a way, you can actually get fits in detail using these, not just the flattening, but the actual transition between Newtonian and non-Newtonian behavior. You also should not be naive. What you get is what you see. That's not just the stars. We know that it's dark matter in the sense of gas, which doesn't shine. There are other ways of finding it. It's not dark in the sense that there's no way of finding it. It doesn't shine in the sense of stars shining. And in a way to get this detailed level of fits between the observations and the prediction of the theory, you need to put everything in, and you actually get more than just the asymptotics. You get the detailed curves, not just the asymptotics. So this is one of the great successes of the theory. Also, you don't go around, you don't introduce a new parameter every time you have a new galaxy.
Can I ask a question?
Yeah?
You're saying that the mass is proportional to velocity. If you go ahead and do it for each of these galaxies, you find that there's a different proportionality constant for each galaxy.
The spread is very small.
Right, and so if you adopt an average value and then try to put the rotation curve back in, you find for none of the galaxies would you get the right rotation curve.
Well, but that's the thing. I mean, so talking about the spread and on the statistical thing, should I put the average in everything? Or should I just? I mean, there is a spread in the observations. There's observational errors.
The point is that the model is engineered to give you the full.
Yeah.
Whereas the observational data, if you look at all the observational data, the index is between 2.5 and 5.
No, that's
So the way you get 4 is to assume an average value for M over L for all the galaxies, which is what we do. Solve this in my problem.
I wouldn't want to get involved in this argument. Anyway. So the thing I was going to tell you more about is, you can actually explain very many different galaxies, and they're quite different in some cases. In some cases, Newtonian behavior and MOND behavior start actually before the flattening can actually happen. It can start after the flattening. In some cases, there's actually a big difference before and after, and you never actually see the flattening. There's already no Newtonian behavior, etc., etc. And well, appreciate this because everything else is much worse. So I think it's fair to say this is the same way that galaxy rotation curves is the point where dark matter fares the worst. This is also the point where MOND fares the best because it's, as you point out, it's actually made to fit the data in the first place. Yeah, sorry, I thought there was a stretch.
No, so for these plots that you have here, is A naught the same?
Yeah.
So you have, so you get a different functional.
So there's a great reluctance in the community of people doing MOND changing A naught. I don't know why. I would have changed it in clusters or in other situations. They have this idea that A naught is a universal constant and never change. Not just A naught, but I'll explain more. But the mu, which is the function which interpolates between these two regimes, is usually fixed. So you don't let yourself change the parameters every time you do a fit.
So I get a different, how do I get a different shapes? That's because I have a different matter distribution, visible matter distribution.
So the profile of accelerations is different. And the thing which triggers different behavior is the acceleration. And that's of course different galaxy from galaxy, but that's not put by hand. That's observed.
The template is sort of the universal.
Sorry?
The template, the function mu is universal.
Yeah, it is universal.
It turns out that recently that when you change mu, stainless being the constant fits are not sensitive to mu. It turns out that's not true. Because,
I think there's a lot more there.
there's a lot of stuff there that you can gloss over.
So this is about ordered behavior, by the way. There's a lot of stuff around which is actually chaotic behavior, like elliptics and so on. So there are galaxies in which this is not true, but we know why it's not true in the first place. This can only, by the way, you can actually show that I was going to do this next. This can't possibly be true in general. This must be tied into a certain level of ordered rotation, spherical symmetry, etc. Because I can actually, as I'll show, prove that this violates energy conservation, momentum conservation, everything else, if I depart from this image.
So you're going to write down explicit form for mu.
Yeah. Okay. So basically, well, I was going to do that in a different form. In fact, I might do that.
What are the blue curves here in the slide?
Sorry?
What were the blue curves?
So I think this is Newtonian prediction. Yeah, it's the Newtonian prediction.
Okay.
You just take gas and stuff, like a Newtonian. This comes from, say, something.
Blue curve must be the, in the core, it's pure and always Newtonian.
Well, my impression is that that's exactly the point. Yeah, this is obviously an unusual.
The blue curve is the hydrogen, the initial hydrogen gas.
That's what I thought at first too, but it's not. In most galaxies, there's no hydrogen gas core at all. So NGC 4013 would make sense either. So I don't think it's the gas.
I don't know the galaxies by name.
It looks like it's some scaled version of the Newtonian result because, as John said, the core, the Newtonian fit is usually correct.
And I think the crucial point is that there are cases in which you don't need to flatten to get non-Newtonian.
So something's been, yes.
By the way, another important point is that the idea always just goes around that you have to get a flattening of the galaxy curves. Many of them are not flat, they're rising.
Yeah.
And this still fits.
Yeah, exactly.
So this myth about flattening,
Yeah.
just because you get
So flattening was the thing which led, basically, the free observation which led to the dynamics. Then, once you have the dynamics, you depart from that, and you basically fit detailed rotation curves, not just asymptotic. Anyway, let me move on. This is obviously a bit of a joke theoretically.
There's a question.
I'm sorry.
If you go 2 slides back, or you have all those results. No, the next one. Yeah. Is it just me, or are there usually points at small distances significantly off? I mean, I don't know, you don't write what you plot on the x-axis, but usually whatever in your units 1 or so, there the points are significant.
I have no idea.
Yeah, I can answer that. The points of the core are off from the prediction because they're quite sensitive to the ratio of M over L. And so, of course, if you just fit to the core, then you calculate an M over L value, which would differ from this average that is calculated throughout the galaxy. So it's very sensitive to the rotation, the acceleration law.
I wouldn't take any of this seriously. To be honest, I think talking to astronomers, people start talking about peaky detail. I think the most worrying thing, to be honest, I mean, of course, as I said, Saturn was completely wrong, and no one cared about that. The Newtonian theory for 100 years. It's completely obvious there's going to be problems here with the predictions from the theory in the first place.
Well, in order to fit the core of a galaxy, I have to question the assumption whether or not M over L is actually constant within a galaxy.
I would question energy conservation first. I mean, I think the most worrying thing about it is that this cannot be a serious prediction when you depart from a certain level of high symmetry. So probably do inside the
That
galaxy.
can be proportional to L on average throughout the galaxy. But would that be true point by point, especially within the core? I know that the stellar population is very different within the core, and perhaps the core has a higher percentage of high luminosity stars compared to the outside. And so M over L may not be constant within the galaxy, although it is constant on average.
So I think worrying about this level of detail only makes sense once you have a full theory. That's the first thing. And I don't think this is a full theory. This is something which is an embarrassing idea, which derives, first of all, from very rough asymptotics in the rotation curves. Then you actually get more than what you bargained for. And then it's not perfect. I know it's not perfect. I wasn't expecting it to be even this perfect, to be very honest with you. And the amazing thing is that there is a mu here, which usually is just something that shows like x. It's actually exactly 1 plus x. Simple mu, which actually works extremely well in detail. But honestly, none of this can actually be, the fundamental theory. First of all, because there's no reason fundamentally to have mu of this form. And second, clearly this is not a theory, it's just a model. And it's a model which has these very serious problems. First of all, if you think a bit about it, you immediately realize that you actually violate momentum conservation. You just take Newton's prediction. So this is something which clearly cannot derive from Lagrangian formalism, for instance, because otherwise it would be built into it, that there is some modest theory version of conservation theory. But more seriously, there are always these contradictions. I mean, suppose I take a small bit of the galaxy. Well, actually, this thing may not be rotating with an acceleration larger than A0, but of course inside there's all kinds of rotations, things are moving around. And the internal motions of an acceleration is actually much bigger than A0. So you have this part-whole paradox, which is not addressed by a model as simple as this one. Or vice versa, you could actually have an environment in which, well, basically the reverse problem. It's called environmental open. It's exactly the opposite of the situation. In other words, the theory has to be, I think this actually shows that the theory has to be nonlinear intrinsically for it to make any sense. And this kind of prescription can only be valid if you have very high symmetry situations. It cannot be valid in general. So this is the first problem. There's other problems, and the theory doesn't fit very well clusters. So this is observational problems, and these may be related. So I wouldn't worry about this kind of level of what happens in this 1 parsec here or there, but it's much worse than that. The theory doesn't fit clusters very well, and this could be related. It could be a practical problem related to the fact that we don't have a theory. We have something which is a phenomenological model. And above all, there is a situation that we have a non-relativistic theory. We'd like to know what is the relativistic version of it. We do know about dark matter via lensing. And if you want to get rid of dark matter in every situation, you should explain why there is extra lensing in a relativistic version of MOND as well. So in summary, I think it's a bit premature to worry about these details, but it's a lot worse, it's a lot more complicated to my mind. I think either you just say MOND is just a very efficient way of parameterizing dark matter inside the galaxy. This could be your attitude. I spend a day a week in CETA, and of course this is everyone's attitude there, because they have a big investment in dark matter. well, here everyone finds dark matter very boring, in which case it should. The question for you is really, what is the serious relativistic theory which replaces this very simplistic prediction? Okay? This is obviously nothing very serious. Theoretically, it's interesting, phenomenologically, and this is how we should take it.
How will you do with clusters if you make this characteristic acceleration slightly
Yeah. So if you change it, you can fit the clusters. Okay? This is why I said there's a reluctance inside the MOND community to change A naught.
Yeah, but the problem is that, apart from the fact that there's no theoretical reason for knowing why acceleration should change, you have to think about the fact that you have a cluster of galaxies. The galaxies inside the cluster have to have A naught, 1.2 times 10 minus 8 centimeters per second squared. But then you're changing the acceleration of the cluster of galaxies. And that's just not logical, because the thing that has correct acceleration to fit the galaxy data has to be different from the clusters. I mean, I don't know if there's any way of
If you make
justifying that.
if you make UL dependent, and they not dependent, and if you make A naught a function of L,
Then you're bringing in a landscape.
yeah, exactly.
Well, thank you,
Which is
because
what you did.
I have to say that
So there's a reluctance inside the community to do that. And I agree with it, because as you're going to see later, if you actually try to put more detail into the model, the theory rather than the model, then lots of surprises can be anyway. And I think you should worry more about perfecting the model and you can start putting in extra parameters. This ends up being like dark matter.
Yeah, exactly. So if you start making an arbitrary function, then I can just say that there is a certain profile, like it or not, for dark matter.
I agree. I agree. So my attitude has been also, stick to the model, try to improve it, keep the new fix.
the idea of having a critical acceleration could be wrong. But if you start with the theory of the landscape, as I
This is very important.
then you
So can I just say something? So this is, again, we have different attitudes about it, and everyone should know.
I have to say,
My attitude is that you should take the bull by the horns. If there is an acceleration there, you shouldn't hide it somewhere inside your calculation. You should put it in the first line of your theory. And then you don't like it, fine. I don't like it either, but that's what it is. Okay.
but you don't have to buy it. In fact, when you do, this is when you get all the troubles.
Well, I mean, the other option is I don't have any problems, because the thing which doesn't have any problems is not the thing which fits the data. So there's two attitudes. I'd rather have the problems there explicitly and state it out because this fits the data that has this problem than hide the problem.
Well, I don't feel I'm hiding the problem.
Well, I feel you are. So it's kind of, we have a different view on this. Anyway, so this is all a bit metaphysical too. So I think at the same time we need to improve the actual theoretical construction. To my mind, I don't know how many astronomers there are in the audience, but I don't think anyone will ever believe astronomers until you actually come up with something which is like a ground-based experiment. And what we need is a direct detection, and this applies both for dark matter and for MOND. So there are two things we need to do. One is improve the theory and actually get something which is an actual theory, or even more serious theory. Secondly, in terms of predictions, I think it would be useful to actually have the counterpart for what would be proof of dark matter. So if these people are doing dark matter searches, when they turn out to find a dark matter particle, what would your attitude be if you're against dark matter? Well, I'm just throwing the towel, personally. And if you find the dark matter, and the dark matter has the right properties for extending structure formation, etc., then
But you will never know. Suppose you find a
I
particle.
think there's a
You'll never
level.
know if it's stable from ground experiment. You have to go for some physical observations.
I think at some level you could do like the Fred Hoyle attitude, which is you never throw in the towel, so it's steady state forever. So I mean, I think it's reasonable that any theory which is a scientific theory has to have a threshold beyond which, okay, forget about it. And to my mind, the thing which, for dark matter, which, there are all these uncertainties and these things, the thing which should basically give the push to dark matter and give a Nobel Prize to people who found it to be very deserved, which will actually detect a part of dark matter.
As he says, how
But even
do you
then,
know you detected it?
no, you can't detect it, but then you don't know if it's stable.
Okay,
Mechanic-
there's this
mechanic
attitude.
kinetics are particles.
So there's another thing which is the other aspect I don't like. Is that there are people, there's actually an industry of people producing dark matter candidates which could never be detected. Some gravitinas and so on. But there's actually, you know, so, and I think that's ridiculous. I mean, you should come up with something which fits well into the particle physics models, and which should be detected. And then, of course, there are these issues. Is the particle we detected here the same one we observe astrophysically, etc., etc.? I mean, and then eventually things would match. But I think the thing that would give it the push would be detection, direct detection. So what I'm going to do in this talk, and the point of this talk is basically about to finish, but anyway, the point of this talk was actually to kind of find the counterpart, and that's what we tried to do in this paper. What would be the equivalent backyard detection for MOND? Is there something inside the solar system which would be essentially proof of MOND in the same way? So let me skip a few details. With no doubts, basically, you need to know that there is indeed a theory. It's extremely ugly, that's all you need to know about it, in which you actually have a Lagrangian formulation for this. The point is that it also has a non-relativistic limit. There's lots of horrible things here, actually, which you don't need if you're going to go into the non-relativistic limit.
But even though we don't need that,
Sorry?
even though we don't need that, but can you comment just
Yeah.
the general features of this?
So this theory, again, maybe since you asked for it,
So I would like to see if there is a limit to Einstein's gravity. What are the leading corrections?
so what you want to know?
In particular, my question is there a limit in this theory in which I have Einstein Hilbert term? And second question is, what was the leading corrections?
So the answer is yes. There's a PPM formalism version of the theory.
And what is the correction? Can you write down the operators, additional operators?
You mean the quantum operators in mind?
No, just classical. You know, the terms. So there
Yeah.
will be Einstein Hilbert term plus.
No, this is not only addressed by PPM parameters, which are indicated. So the same way as parameter twice plus mutual parameters. So that's basically the way you can formulate the corrections.
One worry I would have related to this is whether there are ghosts in this theory.
Yeah.
Okay, I was going to avoid this. So, okay, I was going to skip this, but I'm going to talk about it. This is a biometric theory, by the way. So you should be happy. It's a biometric theory. It's actually a very stereotype theory, although they don't like to stress it, but it is one of the biometric VSL theories. It's an example. And you basically say there are two metrics. One is the matter metric, which couples matter, of course, minimally. And then there's something which is the Einstein metric, which is not conformally related, it's formally related. And in order to do that, introduce the vector field unit. And in order to put the minus here. And you say that you have a transformation which has one factor in the direction of time, of the u, and another one in the spatial direction. Okay, why do you need this for lensing? Okay, if you only had a conformal transformation, lensing would be exactly the same, and we would explain the dark matter in the lensing situation. This is the guy which gives you ghosts, by the way. And even that, I don't think it's been proved. If you don't like it, throw it away. Okay, that's the only thing I can say. So that's exactly there is this conception that MOND phenomenology depends on the vector field. It does. The vector field is there for them, and for cosmology. Okay, that's a different matter. But for the purpose of non-relativistic limit, you don't need the vector field there for anything. Rather, what happens is that the G naught naught, which is from, so what you do is you basically write this guy as -1 plus 2 some kind of physical potential. And of course, this physical potential contains the phi from the Einstein metric, which is the Newtonian potential, and then I call it this phi, and then it contains an extra scalar field phi here. So basically, you have a fifth force, which is the MOND force in these theories.
Does the violation of local variance come from the vector field?
Well, in this theory, I mean, this is the two situations. Either you say this field is dynamic, in which case there's no violation of local variance invariance, but there may be ghosts. Or else you say it's not dynamic, and then there's a violation of local variance invariance. So one or the other.
The minus Norris rings comes from the vector field. Is that the U? Okay. Either way, Least Moore and I checked for the.
I've seen Lee's calculation. He hasn't checked anything. You basically check.
Yes.
You basically check this term. The field appears here, and it appears in various other places.
I did the whole thing. It's not very difficult. You do a Hamilton-Dirac analysis, and you find that the Gauge multiplier makes the Hamiltonian bound for the.
That's here.
Yes, there's no way around
The
it.
field appears there.
You take this action,
Put all the terms together. Because
it's
it's
a
actually,
Hamilton-Dirac analysis, and the theory is unstable.
did you put this term in there?
That doesn't make any
No, but did you
difference.
put the term in there?
Yeah, that makes no difference to the analysis.
Did you put
The
the
problem is the Gauge multiplier.
Did you put the term in there?
Yes, I put the term in.
You swear?
But I did it from my own theory, which is stable. Okay?
Anyway, I'm not married to this. Sorry.
Another question was, is that the most general action with these three concepts?
No. So this is just an
So you
example.
assume a lot of things to be zero.
Yeah. So this is the difference between particle physics attitudes and relativists.
Yeah.
Particle physics always put everything. Whereas relativist cosmologists just put everything you need on it. It's a different attitude. So there's probably there's no tuning for problems if you take things from this point of view.
So if I make the vector field dynamical, will it develop some condensate? Can I fix the model in such a way that I will have like sort of a ghost condensate and then a stable?
That's a very good question, actually. That would be interesting.
Because people discuss that with ghosts.
I mean, honestly, I don't care about ghosts, but these people do.
Well, I think it would be nice if you want to put something on top of this, just saying that this is like an effective field theoretical.
Sure. I just want the only point I wanted to make here, since you asked the question, is I want to dissociate the ghosts, the possibility of the ghost of the vector field, and MOND phenomenology. This is here for lensing, and no one else has a better way to do lensing. I mean, this is the only way I know of doing lensing without dark matter.
I have a way to do
It doesn't work, you know.
I do mine.
It doesn't work.
Leave my time.
It just doesn't work. It doesn't work, and you know it doesn't work.
What doesn't work?
I mean, you cannot just say G 7 times bigger outside the galaxy.
Why
And
not?
therefore we have lensing.
Yes,
G 7 times nucleosynthesis is wrong, everything is wrong.
Totally disagree.
Well, I disagree with you.
Does that reduce to translating theory?
It's similar. Yeah, it's very similar, not like. I mean, the main point is
specific choice of potential.
our scalar tensor. You're saying it's scalar with it.
Yeah, it looks exactly like zero.
Now, the crucial thing here, the thing which is actually hiding in this FE, which makes it very different, is that it's become something called a quadratic Lagrangian for the scalar field. I told you this thing has to be nonlinear. And this is the crucial ingredient. So the vector field you don't need for MOND. What you need is the scalar field for a very funny nonlinear dynamics. So as far as I know, I've never seen a branch digit here with a quadratic Lagrange, a non-quadratic Lagrange.
Well, there's K-essence.
I see, but that's
Yeah.
You're going to
probably
hear about this
related.
afternoon.
But that's probably related to all the terms equal to zero.
Oh, you see, you could put the branch digit on top of it. Well, that is true.
No, I mean you take the most general thing
Yeah,
and you get
sure.
trans.
No, that's true. That is true. Yeah, of course, the branch digit is a conformal transformation.
That's right.
Okay, anyway, let me just...
Why can't you can already keep the perfect in the Swan system?
Sorry?
If you can already be perfect in the Swan system,
Yeah.
then you won't get stuff like preferred frame effects, which also configure in the TPN format.
If I neglect the...
Yeah.
No, I'm saying if you just take it out, I'm not saying neglect it. One thing you could do instead is to forget about vector field. You don't believe in the theory in the first place.
Right, but then
And then lensing is in a better way than this.
no, I'm talking about the PP. I'm
Well,
just talking about
I have the
TPN.
right way to do it.
I don't care about lens, I'm just talking about TPN.
Yeah, yeah.
Right. If you take it out completely, then you're missing some of the effects. Right?
Now, one thing you screw up big time is, of course, the calculations in the cosmological perturbation.
Right.
The PPM is fine. I mean, it's kind of...
But there are certain PPM parameters which are there to give you preferred frame effects.
Oh, with the U or without the U? With the U.
well, you will need to put the U, otherwise you won't get.
Oh, sure. But that's great. We've never seen that, so that's fine. If you just set the U near to 0, that's fine for that.
Yeah, but then maybe the theory predicts strong.
No, yeah. So, okay.
Yeah,
So your question is the opposite. Suppose I put the U there. Do I get an alpha VPN, which is a crucial one? And if I was spin computed, it's not very big. Well, actually, constraints on alpha VPN are not very good, to be honest. Anyway, let me move on. This is really not what I wanted to talk about, but I knew this was going to be like this, actually. So I thought this was going to be a humiliation to each. Thank you very much. Shall we return in kind in the future? Let me talk about this, what I really want. There's not much time, so let me just summarize a few things about this. There. So this is going to be a bit summarized, but let me just. So the basic point, intuitively, let me not give it too many calculations or many things.
You have a lot of time. And we started late.
Okay.
You have 30 minutes.
And that's also part of the
No, this is a big demonstration.
don't stop.
You want to see
So.
You want to see blood or what? Anyway, so the crucial thing is that when you actually reduce the theory to the non-relativistic limit, what you get is rather something like this. I'm going to tell you a bit about this equation, but the crucial thing is you're going to be getting non-Newtonian behavior, not when the acceleration is small, but when the gradient of the potential is much smaller than A naught. This is the total gravitational potential. So inside the solar system, where does the gravitational potential get small? And well, there's several places. I thought about perturbations. I mentioned Neptune initially. So the perturbations actually are in the Mondian regime. Most of the perturbations in the solar system are much smaller than A naught. But I'm going to show you that the stability of the solar system and all these perturbations are not affected at all, because the criterion for MOND behavior is the gradient of the total Newtonian potential, not one component, to be much smaller than A naught. So if you have a small component, here is nonlinear, you have to put everything together. If one component is a gradient which is smaller than A naught, that still is not enough to put it in the Mondian regime. Well, then I thought about Lagrange points. Lagrange points are a generalization of the geostationary orbits. So it's the points in the orbits which basically rotate with the Earth. This is the Sun, that's the Earth. What you find is there's these 5 points, L1, L2. So here you can see you basically have a centrifuge which goes like omega square r. This guy is the biggest centrifuge, but the Earth is pulling it as well. This guy is smaller centrifuge, but the Earth is pulling in the opposite direction, so it balances it exactly. And there's a point here and there which is exactly the balance point. This is the planet X, and if you've heard about this, for a long time people thought it was a planet we couldn't see, but it's exactly the other side of the Sun. And basically it's a stable point as well. It's a bit further out, because it has the extra pull of the Earth. But then there's these funny points, L4 and L5, if you think a bit about it, but they're equilibrium points as well. Maybe this is exactly where we're going to actually detect the theory, but this is not a strong MOND place, and that's because the gravitational potential there's not a zero gradient there, because you have to balance the centrifuge. Okay, which is a very crucial point. Initially, we thought there's all these satellites going to L1 and L2. They're going to be exactly on the Mondian point. They're not, because remember the Earth is rotating around the Sun. Of course, as a result, the force at a given Lagrange point cannot be zero because it must balance the centrifuge exactly. But there's going to be effects, and I'll go back to that. They're not going to be strong MOND effects, but there's going to be small effects on the Lagrange point in the solar system.
So for all of these stable points, I can see at L1.
They're not stable, that's a different stationary points.
Yeah, the stationary points at L1, the forces would cancel, and accelerations would be maybe within the MOND regime. What about L2? Would the forces cancel at that point?
They never cancel, because you always have to balance the centrifuge. So this is actually the effective potential considering centrifugal potential added on. And if you do that, you find that there's actually these 5 points here, but of course, what happens is they keep balancing the gradient of the centrifugal potential with the Newtonian potential. Okay? And you can see they're all unstable. The saddle points really of the effective potential. This guy is a maximum actually. By the way, this guy is a maximum, it's stable. I don't know if I'm going to have time to go into that, so maybe I'll tell you this now. It's a very big surprise, but actually because this is a rotating system, there's a Coriolis force, and we end up with stable orbits around this guy, even though it's a maximum. So the guy tries to fall off the top of the hill, but the Coriolis force brings it back, and you end up with a kidney-shaped orbit. And surprisingly, actually, if you look at the Jupiter orbit, there's a so-called Trojan asteroids. There's a hell of a lot of asteroids sitting around L4 and L5 for Jupiter on stable orbits. So I'm just telling you this because although I probably don't have time to go into this, there's not going to be strong Mondian behavior. There's going to be mild Mondian behavior, as there is everywhere in the solar system, and these 2 points in particular can be very useful. There's one place where there's going to be strong Mondian behavior. That's really what I want to talk about, and that's the actual saddles of the potential. So obviously you cannot have a maximum or a minimum of the potential. The Poisson law will tell you that you have matter there. So you cannot have a maximum or minimum for the potential. But you're going to have saddles, and in between any two bodies, there's going to be a saddle point. So the saddle point specifically is going to be in between the Earth and L1 for this system. So basically, you need to have some force towards the sun here, because you need to balance the centrifuge. There's going to be a point here where there is actually no force at all. And it's the saddle point of the potential. It's rotating around because the Earth is rotating. And therefore, it's not an inertial point. It's not an inertial point because if you put an object there, of course, again, the centrifuge will not be balanced because the force is there. But you could cross it. The main point is that you could actually go through it, and satellites are going to go through it, trying to get to L1, in fact. I'll mention this later on. So this is the basic idea. Let's look at the saddle point, specifically the saddle point between the Earth and the Sun, which is towards L1. And let me tell you a few things about this equation. So this is the basic equation you have to solve. And there's a curious thing here. So the mu is the guy which eventually goes like gradient of phi. Okay? So it's the thing which eventually goes to 1 in the Newtonian regime, goes like gradient of phi when this guy is much smaller than we know. So in this kind of framework, what happens is not that when you reduce to, say, a situation with a lot of symmetry, F becomes ma squared over a naught. What happens instead is that basically you get that the force becomes the square root of the Newtonian force. Because this guy, you basically get a Laplace equation in which the square of the gradient on this side equals this guy. So in other words, what you would get from here, if you say that mu goes like the gradient of phi divided by a naught, is that if you go into the MOND regime, you end up getting something like this. The usual stuff. And therefore, when you take the square root, you also get effectively the same extra factor of r, which allows a flattening of the rotation fields. Okay, so how do you solve this equation? So Jean criticized my paper for being extremely mathematical. It's not very simple. It's just basic vector calculus.
I think it's pretty simple. I was impressed.
Okay.
Not critical.
It wasn't easy. Basically, the crucial thing about these equations is that they're non-linear intrinsically. So the non-relativistic limit is not a linear theory, it's a non-linear theory.
Let me just make a point about this. This is a very, the point is that if you take a body, Landau-Lifshitz, chapter 1, chapter 3, if you take a body, then because of relativity, you can't have the particles be extended. If you show this for a circulated disk, for example. So they have to be quite large, corresponding to delta functions. So since you're taking the square root, you do not get a linear sum delta function masses.
It's much more, yeah.
Which also happens in what I do. There are non-relativistic limit. And I have an explanation for this, and we'll talk about that some other time. But this is an interesting point which Joe correctly emphasizes to me all the time, most of the time. This is an important point, because the reason you do it is to fit the coefficient law. You need, when you square up, b to the fourth has to be proportional to m. And you can only do that if you have this square root of rho in it.
I don't know, I don't understand that. But anyway, let me move on and explain. So as I said, basically, one way to linearize this would be to say there is some quantity, u, which is not the gradient of phi, but which is mu times the gradient of phi, and which behaves like a Newtonian extension. So this is a way of trying and not succeeding, as you see, to sweep the problems under the carpet. So the idea would be, there's a guy u, a variable u, which I wrote over there, with some normalizations, which basically behaves just like a Newtonian extension. And the idea would be the Newtonian force, sorry. And the idea would be to sum all the Newtonian forces first, and then invert this quantity for the physical guy here. So you'd be taking the square root once you value all the u's, or not, depending on whether mu, the total u, puts the mu in the Newtonian regime or not.
What is k? K is a function.
Yeah. So the equations become these, which is really kind of very nice. But then one thing where things go immediately wrong here is exactly the fact that the thing which is actually the gradient of the scalar is this guy, the gradient of the potential is not u. So the curl of u is not 0. Rather, the curl of u divided by mu is the thing which should be 0. And this is a point which is, this is a technical point. But well, there's 2 points here which are technical points, which I'm not fully appreciating. First, the theory is nonlinear. You can play this trick and say the u is basically the thing which behaves like the usual Newtonian extension, and then I should just invert it. You can do that, but then you should add all the components, including the extra-solar system components, before you do that. Here it's intrinsically nonlinear to begin with. Second, there is this problem. You can do that, but then u is not curl-free. And the way to find the curl, which you have to add to this u, is by putting all the sources together and then working out what is the condition for the curl of u divided by mu to be 0. So it's a technical point, but this is exactly where I think sometimes people ignore all these extra terms and so on when you do fits. But the basic point is, this trick is the trick that allows us to solve the theory, but be careful, I always need to add a curl term, an magnetic term, and this term is not 0, except in the case in which you get spherical symmetry. So all the cases of high symmetry we've seen before, you can ignore all these, you can take the square root, blah, 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 all these things. The theory is intrinsically nonlinear, and therefore you have to put it back for a whole set of sources every time you consider a particular situation. Sorry, this one.
What's H?
So H would be any field. Be basically, so you know any curl can be written as the curl of another vector space. So let me tell you what happens. Basically, the equations become, this is another way to write the equation with a different u, but you can see immediately here, you can actually prove it. If you have spherical symmetry, then the gradient of u squared has to be collinear with u, because everything has to be radial. So this guy has to be 0, so the curl of u has to be 0. So indeed, if I have a situation like basically with spherical symmetry, I can ignore the curl term, and you can also prove that the curl term is subdominant when the modulus of 1 is much larger than 1. So by examining the equations, there's 2 things. Basically, I find that this condition, if I redefine the variables in terms of this u, this big U square equals 1 is the border between strong MOND regime and quasi-Newtonian regime. And second, it's also the place where you have to be careful about the curl. So this is just a bit of mathematics. Let me tell you the results, then we can wrap this up. But basically, how big are we talking about? So we're talking about an ellipsoid in between any 2 objects on the saddle. So in this case, that's the Sun and the Earth. If you go to the saddle point, there's an ellipsoid, which is about 400 kilometers across. Inside, you have strong MOND regime, outside you have quasi-Newtonian regime. So there's 2 things. You can actually track satellites to the solar system to a meter. But this is different. He's putting something in a place within a few hundred kilometers. So it's completely different. And this is not an inertial point either. So be careful, because you can go through it, but you cannot exactly sit there. It'll be like a transient thing. It's bigger because of the Earth Moon is about 140 kilometers. It's about 1 million kilometers for the saddle between Jupiter and the Sun. And this is the kind of region in the solar system we're talking about, dividing quasi-Newtonian regime and strong Mondian regime. Well, near the near-Newtonian field, if you go outside this ellipsoid, it doesn't mean you don't. I mean, sometimes you may worry. So, for instance, in the case of the Lagrange points, you're quite far away, so you run indefinitely in this quasi-Newtonian regime. This is the Newtonian field. So the basic idea here was the following. Before I give you all the details, let me tell you what the idea was. You're not going to be measuring forces, you're going to be measuring tidal forces. But in the case of the Newtonian theory, this is the saddle. So this is L1, this is the Earth, this is the Sun, this is the saddle point, and the force goes through zero linearly. And this A is actually the tidal stress at the saddle. So the force is zero, but this is the tidal stress at the saddle, which is finite.
Why is the saddle from Earth? What's the distance between the saddle point and Earth?
Yeah, you can work it out. It's 400,000 kilometers, 300,000 kilometers.
But it's accessible by satellites.
Yes, I'm going to talk about it. So in fact, you have to go through it when you try to get to L1, because you do a series of elliptic orbits that are bigger and bigger until you get there. So you're going to go through the saddle anyway. The idea is that what could happen in MOND? So in MOND, something unusual. There's going to be strong MOND behavior in a region which isn't small. And what kind of strong MOND behavior is it? Well, let me first of all take this naive thing. Let's just take the square root, and then I'll refine this. So the crucial thing is that if you have a linear function and you take the square root, you get something with infinite derivative. And so the tidal stresses are going to diverge at the saddle in MOND, or at least they're going to remain abnormally high in a region which is actually quite big, around the saddle, a few hundred kilometers. So it's not as extreme as it is when you put the curl field on top and all this stuff, but that's the basic idea. So it's actually much more complicated. Let me just tell you, basically, in this case, if you stay outside this ellipsoid, then basically you can solve the equations analytically, surprisingly. You can neatly separate between something which looks like the Newtonian component, which has this profile. So you can actually see what happens. The divergence must be zero. So you have twice the field in this direction than in this direction, but we have two directions. This is the axis, we have an x and a y, these two directions, the divergence must be zero. So basically, it's a saddle point, you fall off in this direction, you actually compress in the opposite directions, which is the trick they're using to put satellites there, to get these mismatching orbits. If you go in the plane which is orthogonal to the ecliptic. And so this is the U0, which is the Newtonian profile field you have. You can easily split into two and basically plug into the equation with this perturbatively in this case outside the ellipsoid. And you find that for a surprise, the B field is not negligible, which is why I don't like people making comparisons between observations and the theory in situations like clusters or satellite galaxies in which you don't actually have exact spherical symmetry. The B field has to be put in, and it shows it very well. It's of the same order of magnitude as the field you will obtain by taking the square root in the first place. So you can make a prediction. Here it is. Let me just give you the numbers. This is the profile we find when you put everything together. Around the saddle point, but outside strong Mondian regime, you get this kind of field, and you can actually detect the B field component quite easily by eye. Basically, so in the case of the Earth, 400 kilometers away from the saddle point, you get a correction which is about 0.25% for Newtonian gravity, and then it falls off like 1 over r squared, because the Newtonian component goes like r, and this goes like 1 over r. So basically, the fraction component goes like 1 over r squared. So this is not small. Okay? This is always talking about 0.25% in tidal stresses, even if you stay outside this ellipsoid where we have strong Mondian behavior. If you go into the inner region, it's a complete nightmare. In fact, we have to do this numerically, semi-analytically, numerically. You find that you can't even dissociate the curl term from the other term, and in fact, numerically, you find that you have a profile in this U. Before you take the square root, as people usually do, you have to put the curl term on top, and what you obtain is something which does not go like R, as you would expect, without the curl term. It goes like something which goes like R to 1.5. So the tidal stresses still diverge because, essentially, if you take the square root of something, with a beta which is smaller than 2, you still get a divergence. But it's not as dramatic as you would get by neglecting the curl term. So qualitatively, you get the right picture from here. The tidal stresses are going to be high. They're not going to be completely crazy once you put the curl term in.
What about, back to your point about the fact that since you're not adding the masses linearly, what about the conservation of energy?
It's conserved. This comes from a Lagrange.
This is the
What mass?
This is Santa's Frankenstein Lagrange.
No, this theory reduces to equal anyway, in the relativistic regime.
So you do conserve.
Yeah.
This is the 84.
You reduce it to that metric extension. Let me give you a picture as well. So the crucial point, you have a profile which is actually very similar to the Newtonian profile. And the idea is indeed, when you take the square root of the field which looks like the Newtonian field, but the crucial difference is that the radial distance is slightly different.
Sorry, can I ask you a question?
Yeah.
So these predictions for the deviation of the force were obtained with some specific value of A naught.
Mm-hmm.
So is the value of A naught the one you choose is the one that's from the clusters?
No, one from galaxy.
From galaxy rotation.
Yeah.
So don't you have to reanalyze those pictures now, including your curl and contribution?
So in that case,
see whether you get whatever values of sure. I not you have to choose.
So I'm not worried about that unless, so the only claim where I've seen of triaxial galaxy structure is basically the guys trying to do dark matter fields. I think you're fine in the galaxy. The cluster I'm not so sure. And particularly situations like, satellite galaxies where you have many body situations and so on. I mean, I would also not trust the curl term to being 0 in that case.
What's the scaling of this correction with A naught? So I guess my point is, suppose that is not observed. So that will push you to some values of A naught. You can still sort of save the MOND theory provided you put A naught.
No, because you wouldn't be able to fit the galaxy projection. So this is all fit. So there are parameters in the theory, you fit them to the galaxy in that state.
I guess I'm more like thinking that I'm going to give up the universality of A naught. So
yeah,
how much I have to give up before?
Yeah, sure. So all these predictions are, I think I'm going to tell you more specifically later.
Just the scaling with A naught, so it must vanish when A naught.
I'm going to give you some numbers. Okay, actually very soon, when I talk about the actual observation.
There's no evidence for lack of spherical symmetry of clusters of galaxies. People have looked for this during the lensing.
Well, the X-rays are very far from spherical. The X-rays are not the point. If you actually look at the thing around, they're not spherical.
When we do the lensing, people have tried to find this, and there's no evidence for any triaxiality.
That's not the point of what I'm going to say. That's a different topic.
This question was asked.
So anyway, let me just kind of summarize. So there's all these mathematical things which are not known before. If you're going to go to the satellite guys, and I'm going to tell you this is the prediction. You have to do the calculation properly to give it. And this means putting the curl term there, and this means not just taking the square root of the Newtonian potential. And what you find is it's quite easy to distinguish these two regions. There's going to be a quasi-Newtonian region and a strong MOND region. In the strong MOND region, the thing you take the square root of doesn't go like R, and therefore the divergence of the tidal stresses are significantly lower. Still, basically what happens is that you have this ellipsoid, this is the Earth, there's this ellipsoid surrounding the saddle. The corrections follow, the fractional corrections, delta F over F, to Newtonian gravity, fall off like 1 over R squared outside. But here, they actually grow like a power of R to minus 1.4. So they diverge a little bit more softly than what you might have naively expected. And on the border, we're about 0.25%. So this is the kind of order of magnitude we're talking about. So, what can you do? Well, what does it cause? What kind of perturbations does it cause? This is the equivalent of a perturbation caused by a small asteroid. This is Eros. It's one of the smallest asteroids we've known. You can feel the gravity of this thing that is quite difficult. We're talking about a small perturbation, but in any case, the point is you really have to go to the right place. And this is something which may be happening with the guys who are testing technology for the LISA satellite. So as you know, there is gravitational wave detector which should be launched at some point in the future. The question is whether the technology is well tested already. There's a precursor called Visapath Finder, who's going to be doing most of the testing. And it should be launched next year. And what they're going to do is they're going to put the satellite in an orbit around L1 by a series of elliptic orbits, which will indeed pass the saddle point, and then eventually get to L1. Now, this thing is incredibly sensitive because, of course, what they're doing is they've got these interferometers. And what they're doing is essentially something which measures tidal stresses with a given precision, a given acceleration. Usually, the problem with these things is radiation pressure. So very close to the sun, things are not really free-falling because you have radiation pressure. The technology they're developing is you have these proof masses inside, they're encased. So the satellite has to bear the radiation pressure. But what the satellite does is actually tracks the proof masses inside and adjusts for the radiation pressure, which itself is filming. So this is, as far as I know, the only way to actually measure very accurately free-falling masses very close to the sun. So this technology of basically putting all the proof masses inside, shielding them very carefully, then tracking them and correcting. The kind of accuracy, the kind of sensitivities we're talking about is 10 to the minus 15, second minus 2. These things are a meter apart. So we're talking about acceleration of 10 to the minus 15 meters per second minus 2, which is 5 orders of magnitude below the MOND A0, okay? So what you can do is, with this picture I gave you, so the actual tidal stress is 10 to the minus 11 at the saddle. You can compute it. So we're talking about corrections, which basically are 0.25% within about 300 kilometers, then follow up like 1 over r squared, then increase like 1 over r to this kind of power. So you can actually work out what is the target area for something like Visapath Finder. You can't sit there, you can't sit on the saddle as you've seen, but you can actually work out, it's not a small target area, it's about 4,000 kilometers across. So you will go through it, actually. And the issue is whether or not you should be able to go close enough to the saddle accidentally. You're going to be tracking things within a meter. Of course, you're not trying to get there. You're going to be tracking things. And you'll be passing the rough neighborhood of these. You can work out the effect in the Lagrange points as well. It's much smaller, so it's much more complicated. Once you get to the Lagrange points, try and find the effect. You shift L1 by about a meter or so, 4 meters or so. The question is more like the orbits around. There's these Lissajous orbits that are a bit shifted as well. So there is a chance you may be able to find these things later, but that's less likely. In my mind, you're going to get the backyard detection of MOND. It's going to be something basically going through the saddle and basically hit the numbers you're talking about. So I'll close here, and I'll just say that, so this is basically what I wanted to tell you earlier on about the Lagrange points. Actually, seeing the divergence, that's a bit more complicated, because then you're talking about a really small region, which is not inertial, but what could actually happen, which is what I'm working on at the moment, is if you have something like a diffuse medium, and the saddle is moving around the diffuse medium, then you will actually impart structure from the medium, even though the saddle is not inertial itself. And an example is the rings of Saturn. There's all this crazy microstructure in it. People understand some of it, but not all of it. And I've been looking at all the possible saddles, seeing whether or not it could be the movement of one of the saddles going through it, and the divergence of the tidal stress causing out this small structure. And that's basically it. I should wrap up here and a few more things to tell you, but let me just pioneer again. Anyway, conclusions. I think the main point is, in any case, in any theory, it's just common scientific decency to set up a criterion from when is it exactly that you throw in the towel? So there must be proof reasonable doubt, and there must be a point of throwing in the towel at some stage. So there's all these issues about dark matter. Is dark matter an ether or not? I didn't talk about the other areas where dark matter is very successful, such as structure formation. It certainly has problems with the galaxy rotation curves. But I think everyone doing MOND should think about something like, or anything equivalent, something like the equivalent of a detection of dark matter. So something in the backyard, which should be like the equivalent of a backyard detection. I think it should be of concern to everyone, as I pointed out, even if your interests are very theoretical, you're doing string theory or whatever, then it certainly is quite worrying that the classical theory could be completely wrong, even before you start worrying about unifications and quantizing and all this stuff. So this is a possibility. If your work is based on relativity, pray very hard that dark matter exists, because this could actually be quite a nightmare. No one really knows what would be the theory, though. I mean, all these things are not serious theories, to be very honest, but they're interesting ideas. And they throw in lots of interesting things, like nonlinearity. What's the role of nonlinearity in gravitational physics? It's actually quite different from the nonlinearities you have in GR. By the way, not raising issues of delta functions in GR. So. But anyway, I think, to finish, I've worked on dark matter quite a lot. This is my first project on MOND. I think it need to be a bit masochistic to work on anything which is not dark matter. I think someone here might agree as well. It's actually much more difficult to do calculations in MOND. And it's more beautiful to say that it's the gravity. But when you actually come down to doing calculations, still I think dark matter is a much easier way to compute things and make predictions. I think I'll stop here.
Regarding the equations of motions for Bekenstein's theory, does there exist an equivalent to the Schwarzschild solution, square-root symmetric static?
I think, actually, I didn't read the paper. There's a paper.
Yeah. Yeah, there is, and it's not unique.
Oh. So if you choose your vector field, that makes it unique.
Yeah, I think the non-uniqueness has to do with what is the solution for the field.
So who looked up it?
Janius.
We're in this peculiar situation. By the way, it took 1,500 years to go from the geocentric theory of the planetary system to solve the heliocentric theory. We shouldn't forget that. That's a long time to go from a model of the universe with the Earth at the center of the universe to what we know today is true. Everything rotates around the sun, the solar system. So let's hope we don't have to wait 1,300 years to resolve this problem. I won't be around anyway. So, when I've been immersed in all the cosmology, trying to get rid of dark matter cosmology for the last 2 or 3 months. And I come out of all this discouraged, because whereas the MOND fits, and my theory fits the galaxies work very well. For us, it's over 100 galaxies now in the clusters. You can't do the acoustical oscillation piece in the power spectrum. W back and boomerang.
Can you? Can't do a bacon.
Well, we've had discussions about this.
No, I think
you have to introduce a particle which hasn't been seen. In the Frankenstein one, it's the vector field and the scalar field. These particles have not been detected.
They're not particles. I mean, no one is trying to quantize these things. That's the crucial point. No one is taking these things to a seriousness level where you quantize them.
No, but if you calculate the acoustical peaks and you want to get the third peak, you need something else besides baryons and photons. It's bottom line. So as soon as you put something else in, for example, my theory, I put in a vector field. then you've got a particle that hasn't been seeded. So you can argue that you're putting that in to get the third peak.
No, you have the field which has been seen, which is different.
Field, what do you mean that the field has a particle
No.
interpretation?
No.
Unless it's a Bose-Einstein function.
And it's not
Which
just
is
that.
a wave function.
You don't raise the question about the gravity and still fit periodic of Mercury precession with relativity. So I think it's kind of, we're talking about different levels of things. This is talking about gravity, not talking about particle physics.
Well, you have to talk about particle physics. You know, related baryon, the galaxy fits are done with baryons and hydrogen, for instance, particle physics. So there's this issue. So I've come to a compromise position where I have some dark matter, Bose-Einstein quantum etc. in cosmology. And when I come to locally bound systems like galaxies and clusters, then baryons dominate. But this is the way it suits. Unless there's something seriously wrong with the dubbing method.
There is something seriously wrong with that. By the way, it should be released within a few weeks now. It should be released within a few weeks now, otherwise I'm going to get money for the next.
Why is it we don't get that data?
Because there's something seriously wrong. I mean, if you actually download it, if you've ever worked with the WMAP data, you know that anyway.
You have?
Yes, I know.
You're an expert.
No, but I know there's something wrong with it.
More than the rest of us.
I maybe stupid question. I have no idea about dark matter. So, if I want to use dark matter, what is the status of dark matter in our solar system? And are there some special property? Would there be some special class of the dark matter near these Lagrange points? And I guess my question is there some of this concluded that how unique are MOND predictions compared to if I want to mimic the same observations?
They're completely unique. There's no way you could get divergences of tidal stresses because. But the subtle points are not even. They're not even stationary points. I mean,
okay, so there couldn't be any. Okay, good. That's sense.
But in any case, you could go there and check. Just so yes, okay, complete.
But there is no dark matter in the solar system.
There is what?
There is no dark matter in the
Okay,
solar
also
system.
there is
Papers have been published showing that, for example, the Klein Alexander anomaly, which is 4 orders of magnitude in acceleration per 1 meter. If you try to explain it with dark matter, you would destroy the solar system.
Solar system is a very fickle thing. I mean, so one thing I didn't have time to say is that all of this has been Mickey Mouse, very Mickey Mouse kind of picture. In practice, the solar system is an embodied situation. There's like, there are codes tracking stuff, all the asteroids, you got about 1 million objects. So there's a lot of stuff, and we know where it is. If you go to the JPL webpage, you can actually download these codes. So if I ask you the question, where are the satellites in the solar system, I actually have to do the calculation properly. It's not just the sun and the earth, everything is very complicated, and you have to put everything in there. But it's a question which is basically Newtonian physics. It's basically space science. It's been solved. So it's actually very difficult to find something unusual in the solar system. So the effect of this guy, for example, is felt, and you can actually work out and measure it. So I don't see why you shouldn't be able to find the equivalent thing from one as well. And then it would be very difficult to explain this with, some extra asteroid or something.
Sorry, one question, maybe a bit late, but you talk about the larger satellites. Will they be taking data while they're transferring to their final orbit?
This is under discussion. But they should be taking data. I mean, normally these things start taking data, at least calibrations and so on, before they get there. So WMAP started taking data long before they got to L2. So, yeah.
There was actually an anomaly in the orbit of WMAP as well as L2.
I'm looking into this. Yeah, but this is L2. I mean, that's a completely different thing. I mean, you have to.
That would have to be a sizable force to have pushed it off its orbit.
You can work out the effects of the orbits. These orbits are very funny because if you go into the plane which is orthogonal to this, you basically find that you have an effective potential which has different curvature in this direction, and in the direction opposite. So you end up with these Lissajous figures in which basically, because the frequencies are not irrational, proportion they never thought. Now these things are great because actually tiniest deviation and you'll see them. So basically if you look at Lissajous figures with perturbations like the non perturbations, eventually you'll see them. You'll see these perturbations. Problem is that you can never stay on these orbits for more than 6 months unless you start heating them with fuel, basically, with thrusts. At which point you screw everything up, of course, we're no longer free falling. Which is why I was interested in the Trojans, because the Trojans are actually stable. Because the things go around like, continuously. So it'd be easier in a way to track the effect on Trojans than on satellites.
How close would Venus pass to L1 with that curve?
You can work with that. So this is the thing I was saying earlier on. And everything, asteroids and so on, you can actually, there are codes which basically track all these things. And if I want to ever, so basically all I need to know is where the saddles of the Newtonian potential are, and I know where they are. And then I put the model one on top, move it there. And the Newtonian problem has been solved completely. I mean, one thing is predicting in 10 years where they're going to be, that's different, it's a chaotic system. But at a given time, finding out where everything is, it's not a problem.
Isn't the Lagrangian sums of vector sums, they have to modify it because it's not causal. So they produce what we call the coupled phase model. There's a problem with that.
Well, there's at
There's
least
many different models.
there are at least 2 people in this room who have worked on various speed of light theory. So
This is a microscope.
no, it's not. I mean, no one has ever seen waves of this field. No one has ever seen this field, let alone waves of this field propagation. If this field propagates faster than light, okay. This is my attitude. I mean, in a way, it's great. In fact, you could set up a BSL model of your universe with this.
So the BSL model is in the first fraction of a second in the universe, not in the solar system. I know what the speed of light is in the solar system.
But not on the 5 field. Have you seen the 5 field propagating like the wave?
We have to try to keep ourselves reasonably conservative while we're being revolutionary.
Speak for yourself.
Thank you, Joe, again.